Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera everyone. Welcome back on the recorded video. This time we will talking about the localized pi electron. Before we go further to discuss about these topics from the title, we can have some idea what is pi electron. If you still remember in our previous video, pi electrons, this pi electron, it should be uh, py versus, pi electron, it should be py or pz. Okay. Pi electrons, you should remember, pi electron is a p orbital. The pi electrons from the py or pz. Another important point regarding pi electrons is pi electrons are those from unhybridized orbital. So another term is delocalized. What is delocalized? Delocalized referring the pi electrons is not static in the same position. The pi electron should be mobilized. The pi electron should be moving around the molecule. First, if we have delocalized, of course, we have localized electron. So localized electrons, it can be sigma or it can be pi electron. Localized meaning that these sigma in pi are associated totally with the two atoms that form the bonding. Associated totally meaning that it's belong 100% between the two atoms. This is one of the example of the molecule. As you can see, this molecule have sigma electrons. Why sigma electrons? Because all the bonds in molecule are single bonding. So single is one sigma. If we have double bond, one is sigma, one is pi. If we have a triple bonding, one sigma to pi. Come back to this molecule, all the bondings are single bond, meaning that all the sigma electrons are localized electrons. Localized, this sigma is associated totally between two atoms, between this carbon and this hydrogen. Or this sigma is only totally associated between this carbon and this hydrogen. Or this sigma is totally associated between this carbon and this carbon. We go through another example. This molecule, they have double bonding. The sigma component, all the sigma electron are totally associated between two atoms. For example, this one, this sigma carbon and hydrogen, this sigma carbon and hydrogen. This sigma also in the double bonding is associated between carbon and carbon. In the pi also associated totally between carbon and carbon. Another example involving three bondings is the sigma or the pi electrons all are localized. The pi between the carbon-carbon, the sigma also can be carbon and carbon. This sigma also can be hydrogen and carbon. So what is the localized electron? Delocalized is meaning that the electron is moving. So for the delocalized electron is only pi electron. Pi electrons, py or pz, it should be spread over the number of atoms in a molecule rather than localized between a pair of atoms. We see in this diagram for this particular example, which is benzene. As you can see, all the sigma, either the sigma between the carbon and hydrogen, or the sigma between carbon and carbon, uh, the sigma component are localized. However, if you observe carefully for the double bonding, as I mentioned just now, double it has a sigma in a pi. But in this particular example, the pi component is a bit different compared to the pi component in this molecule or the pi component in this molecule. What you can see is the pi component is in this ring structure, the pi component can move. The pi component can spread. The pi electron can moving. For this molecule, this pi here, here, and here. However, the pi also can be moved either here, here, or here. Okay. So the moving of pi electron can be represented by this circle. So during your study SPM diploma or foundation for the benzene structure, normally you draw like this. Benzene, and then you put a circle in the middle. The circle is represent the pi. Because the pi can move from one atom to another, this is why we draw it in a circle form. Okay. Remember, in many molecules, most of the molecule, we cannot adequately describe the bonding is being entirely localized. Some bonding can be delocalized. Localized only a sigma or a pi electron, most of the cases in aliphatic compound. Aliphatic, a straight change hydrocarbon structure. This situation arises particularly in molecules that have two or more resonant structure involving pi bonds. Resonant structure meaning that the molecule can have more than one structure. This structure, it can be drawn like this in another structure, but they are same. This is benzene, this is also benzene. So meaning that this is the resonance structure of benzene. It consists one or more resonant structure. So most of the molecule have with resonance structure, it can have the delocalized pi bonding. So we go very detail the particular example for benzene. We try to understand the delocalized pi electron in benzene. This is the structure, the resonance structure of benzene. As I explained just now, the difference is only the position of the pi component, the pi electron, here, 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 or here, here, here. Okay. If the resonance structure involves the placement of double bonds in different locations, meaning that the pi component, the pi electron of the double bonding is actually delocalized. How it's delocalized is suggested by the resonance structure. In each structure, either this structure or this structure, the geometry of carbon atom is trigonal planar, which implies the sp2 hybridization of the carbon atom. You should remember how to determine the geometry, how to determine the hybridization. For this particular example, because of this carbon atom, we know in order to determine the geometry in hybridization, we should calculate the electron domain. Electron domain is a bonding pair plus lone pair. For this carbon, electron pair is 1, 2, 3. And then how many lone pair is 0. So the electron domain is become 3. When it's 3, the hybridization is should be sp2, or the geometry should be trigonal planar. If you still have difficulty to understand how do we determine the geometry in hybridization, please have a look my previous recorded video on the geometry and also hybridization. So from the resonance structure of the benzene just now, we can conclude they have the sp2 hybrid orbital used to construct 6 localized carbon-carbon sigma and 6 localized carbon-hydrogen sigma in the each resonance structure. The 6 localized carbon-carbon is this one, because this is a sigma, this is a pi. This is a sigma, this is a pi. This is sigma, this is sigma, this is, sorry, this is pi. Okay, this is pi, sigma and pi. And the carbon in hydrogen, because of single bonding, is a sigma, 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 sigma. If you count, you find out it has 6 carbon hydrogen sigma, 1, 2, 3, 4, 5, 6. 6 carbon sigma, sigma 1, 2, 3, 4, 5, 6. All right. And then what next? It's look like this. Okay, all the single bonding sigma. Sigma in this structure can be carbon-carbon sigma or carbon-hydrogen sigma. All these carbon-hydrogen, carbon-carbon sigma, all these localized. Localized meaning that the electron is not moving. The unhybridized 2p orbital of carbon atom can be used to make pi bonding. As I mentioned to you, pi px px py. Sorry, pi it should be py py and pz pz, and also the pi it should be unhybridized orbital. Okay, so it's look like this. This is the unhybridized orbital. This unhybridized can form a pi bonding. So this PY will be combined with this neighbor to form pi. Or this one can be combined with this to form another pi, or this one can form another pi. It's not necessary for this pi component share with the right hand side pi, but this pi also can form here. Okay, this one with this one, or this one with this one, this one and with this one. This is why the pi component can be moving around the atom, or it can move, it can spread over the atom. These pi electrons are delocalized over the 6 carbon-carbon bonding as shown in the figure below. So the pi component in benzene is moved around. So it's a conclusion, the pi component, they have 3 delocalized carbon-carbon pi in resonance structure. With the 3 delocalized, this one. This is 3. Where they? Okay. 1, 2, 3. 3 between carbon-carbon, carbon-carbon, carbon-carbon. 3 delocalized carbon-carbon by bonding. All right. So we done with benzene. The last example is ozone. So what is ozone? Ozone is the chemical formula of O3. So we try to observe the delocalized of pi electron in ozone. If we draw the Lewis structure, it looks like this. This is the ozone or 3. As you can see, each resonance structure, it has 2 sigma and also 1 pi. The pi component, it can be also can be in this position, either in that position or it can be in this position. So the pi component can move over the atoms. This is why we call it the localized pi electron. The same if the resonance structure involve the placement of double bonds in different location, the pi component of the double bondings actually delocalized in a way of the resonance structure, sometime here or sometime here. This is resonance structure. In each of the structure, the geometry of oxygen prime can be trigonal planar. Why is trigonal planar? Because electron domain of 3, 2 bonding pair, 1 lone pair, 2 plus 1 is 3, 3 is trigonal planar, and then is the sp2 hybridization of the oxygen prime. The sp2 hybrid orbital are used to construct 2 localized oxygen sigma. So oxygen sigma, this is oxygen sigma, oxygen sigma 2, oxygen sigma. And then the unhybridized 2p orbital of the oxygen atom could be used to make the pi bonding. These pi electrons are delocalized over the 3 oxygen. So it can be moved between this or this one. It can be here or it can be here. Okay. So this dotted line indicating the localized of the pi component in ozone. As a conclusion, there is the delocalized of oxygen by bonding in each of the resonance structure. So for this particular topic, which is a valence bond theory, uh, the valence bond theory, as you can understand, it should be what in the valence bond theory. We just do the recap. We do the recap. Sorry. We do the recap. What is the valence bond theory? Okay. Just a very quick recap. Valence bond theory here is previously we discussed the chemical bonding from the molecular formula up to the VSCPR model. We decide the molecular geometry. In the valence bond theory, as we know, we represent the overlapping between two atoms using atomic orbital atomic orbital of s, p, d, f sometimes. So we show the formation of bonding by overlapping the respective atomic orbital. All right, we done this. One is 1s, one is ss, sp, also pp orbital. So we do the overlapping of atomic orbital in the hydrogen molecule. Again and again, you should be able to draw the energy diagram of the valence electron. Show the diagram, the overlapping of the atomic orbital 1s, 1s. Okay, another example, hydrogen fluoride. The valence bond theory is just to is a way to identify which orbital involved in the formation of bonding, like this, the 1s1 and also 2p1. S orbital and p orbital to form the HF. For the oxygen, same goes for the oxygen. This orbital overlap this orbital, this orbital overlap this orbital to form oxygen double bonding. This one. Triple bonding, and also in the overlapping region, we will find out two valence electron, opposite spin, up and down, up and down, up and down, and also up and down. So the major part in this topic is the hybridization. You should be understand what is the reason to have hybridization. What is hybridization? Apa yang dimaksudkan dengan hybridization? Apa yang dimaksudkan dengan hybrid orbital? How the hybrid orbital different compared to the atomic orbital? Okay, so we already covered this one. We have the sp hybridization, sp2, sp3, sp3d, and also sp3d2. How to determine? We are using the electron domain geometry. This means that before we decide the hybridization, we have to count the electron domain, bonding pair plus lone pair. This is the way, or this is the procedure how to determine the hybridization. Electron domain of 2, electron domain of 3, 4, 5, and 6. So we go very detailed before to explain the every type of hybridization. SP, you should be able to identify the type of hybridization, and also you have to be able to draw the energy level diagram for that particular hybridization. Last but not least, you have to be able to draw the resultant of the hybridization. Okay, right? So if you want to know more detail regarding the hybridization, please refer the previous video. So we do the sp2, and then we do the sp3. For the sp3, we also focus on the how to do the hybridization of sp3 with the presence of lone pair in this ammonia one lone pair, and also in the water two lone pairs. So you have to be very careful with the energy level diagram for the sp3 with lone pair. It's a bit different. And sp3d, last but not least, we do the sp3d2. The second last subtopic is the overlapping of the atomic orbital. We try to understand in terms of sigma in pi, single bonding sigma, double bonding 1 sigma 1 pi, triple bonding 1 sigma 2 pi. We know how to calculate, how to count, how many sigma, how many pi, and then how the sigma can be formed, SS or PX or S with PX. And also we focus on the pi bonding, PY, and also PZ. So in variable molecule given in the question, you should can tell how many sigma, how many pi. Okay. This is a compound with double bonding. This one compound with triple bonding. And for the pi component, uh, be careful with this pi component, the half fill unhybridized can form the pi component. So please refer again the previous video. How do we discuss the formation of the pi bonding by using the unhybridized? All right. This one is the delocalized pi electron. I just explained just now. Delocalized pi, localized electron, and also delocalized electron. So we go very detailed. To example, benzene and also oxygen. Sorry, and also ozone. So by doing so, I think we done with this chapter. So it's enough for this video. See you again on the another chapter with another video. Thank you very much.